All right, let's do homogeneous transformation matrices. One of the reasons why I want to jump to this now is I want to combine rotation and translation, because I need to use both of those operations to be able to place a rigid body anywhere I like in the world, right? Because these, remember, these are the movable parts of our model, the movable models. So one way to achieve that is to do rotation followed by translate. So in other words, I get my transformed point x prime, y prime, z prime by multiplying out this rotation matrix R, which I'll just again not write all the entries in, but I'll just put points here. So that's a valid rotation matrix, and then x, y, z is my 3D point that I would like to rotate. Okay, we agree that that's just simple rotation that we've been doing using the matrix, and now I add to it some translation that I want to do. I was using this notation last time. I used xt, yt, and zt for translation. So if I go ahead and do this, I should be able to generate any position and orientation for the rigid body. How many degrees of freedom do I have here? 6, correct? So I have 3 different parameters here I can apply for translation, and then I have 3 independent parameters I can apply in here after we satisfy all those constraints I gave last time for rotation, right? So that gives a full 6 degrees of freedom. Again, we could do this part of the computation using quaternions, but I'm doing all matrices today at this point because of some of the particular transformations I'll be getting into. There are interesting questions then about when to convert to quaternions and why at different various times. So one thing to note is that the rotation part is a standard linear transformation, but this addition part comes outside of that because I'm not multiplying a matrix here in the front, right? So I'm not multiplying and adding matrices. I do not have a simple equation of the form y equals ax. I've added some extra term to it. So one simple trick that people like to do is just extend the matrix by 1 dimension, add another row, add another column, and then you can get this expression into a form that looks like this, where there's just a single matrix. So it's just a kind of, let's say, mathematical or algebraic hack, and we end up getting something that's algebraic equivalent. So let me just, there's no real magic to it other than just recognize that it algebraically computes the same thing. There are some deeper interpretations having to do with projective geometry, but I don't need to go into that for this part. So we make a 4 by 4 matrix. That is algebraically equivalent when applied to a point. So what I do is I take my x, y, z point over here when I just applied the rotation and translation in the standard way. My point is just x, y, z. Over here I'm going to extend the vector by 1 dimension and just put a 1 at the end. So I'm going to have the point look like this. I'll put a 1 at the end, but I will just know that this 1 is something extra that I'm using to perform an algebraic trick. So I'm not really increasing the dimension of the point itself. And then I'm going to calculate some x prime, y prime, z prime, and the result's going to be 1 for that. I now have a 4 by 4 matrix, and the upper left 3 by 3 component is just going to be the rotation matrix. So this will be the rotation matrix R. Just copy it exactly from here and place it in, and then I'm going to take my translation parts and put them down here, xt, yt, zt. And the bottom row is going to look like the a piece of the identity matrix. So it'll be 0, 0, 0, 1. And then I'll apply this matrix to my new 4-dimensional vector x, y, z, 1. So if I go ahead and perform this multiplication now, do we believe that we get the same result as we would from performing this multiplication, right? It shouldn't take too much to see the algebra of that. For example, if I just look at the calculation of x prime, I get the upper row of the rotation matrix, the first row of the rotation matrix applied to this column x, y, z here, right? So that gives me exactly the rotation part. And then because I'm carrying this 1 along here, right, I get, because I'm carrying this 1 here, this 1 will multiply with this xt and just add it on, right? When I take this inner product between this 4-dimensional row and this 4-dimensional column, I add on this xt. That's exactly what I get over here, right? I'm just adding on this xt for the translation. So it's just a very simple hack that converts it into what's called homogeneous form. So this is a homogeneous linear transformation. And if, by the way, you want to add some extra part to it where there's an offset vector, then this is called an affine transformation. It has very different properties, and sometimes it's difficult to work with, and you know, it's algebraically a bit different. So if you want to start chaining matrices together and have there be translations and rotations happening all the time, then you don't have to switch operations. You don't have to sometimes add on a vector, sometimes multiply by a matrix. If you use homogeneous transformation matrices, then you're always just multiplying matrices to achieve both rotations and translations. So that makes it very nice. People who do who work in computer graphics, who want to code algorithms very efficiently in, say, GPUs, would like to use the same piece of code or the same circuitry, let's say, over and over again. So that's another motivation for putting everything into one standard form and just performing the same algebra every time. I have an interesting question for you now. What's the inverse of this? Right? So this is a homogeneous transformation matrix, this 4 by 4, that performs rotation followed by translation. Well, before I ask about the inverse completely, though, before you answer that, we should also understand what is the axis of rotation here, right? So if I translate first and then rotate, is that the same as rotating and then translating, right? So if I translate first, then I've effectively moved the axis of rotation. So you could do that. You could consistently go and define things that way. But we're going to do it in the easier to interpret way, which is first apply the rotation so that when we think about the axis angle representation, we're rotating exactly about that axis in the axis angle representation. So you grab the book here. So if this were the origin, you first apply the rotation and then translate it somewhere. If you were first to translate it somewhere, then the rotation would be offset by quite a bit, right, depending on how large this displacement was that was induced by the translation. So just something to pay attention to. All right, so these operations do not commute. So if I take the inverse of this, I need to pay attention to that. So just something to warn you about. All right, so what is T inverse? And I haven't written exactly what T is. T is this 4 by 4 matrix here. So I'll say T is the 4 by 4 matrix. So this part here, that's just the matrix T. So what is T inverse? Let me write a candidate for it. So is T inverse equal to, well, why don't I just invert the rotation matrix? What's the inverse of a rotation matrix? Just a transpose, right? So this only happens for what are called orthogonal matrices. And orthogonal matrices are also have you might want to call them orthonormal matrices because the columns have been normalized as well. So not only are they orthogonal columns, but the lengths are normalized as well, the magnitude of the column vectors. And so if I do that, I could just maybe, let's say, take the 3 by 3 part here, and I'll just put R transpose in there because R transpose equals R inverse. That doesn't work for general matrices, but it works here. So we can go ahead and do that. And now let's see, why don't I just negate the translation? So I could that's the inverse translation, right? If I move forward 5 meters, the inverse of that is moving backwards 5 meters. So why don't I just negate that? So I can go minus xt minus yt minus zt, and then I complete the rest of this matrix 0, 0, 0, 1. How's that? Is that the inverse?
No,
Why not?
because it's having the operation in the wrong order.
Okay, very good, very good. So the operation's in the wrong order here. So if you apply this matrix, it's going to first unrotate and then untranslate, right? Or first inverse rotate if you like, and then inverse translate. That seems fine except for that point that I made a little bit earlier. When you have non-commutative algebra, you have to swap the order of operations when you take an inverse, right? You have to invert the order of operations. So this is not going to work. So the answer is no for that. So let's write what the inverse actually is. It's very helpful to observe these kinds of things when you're writing code, when you're doing development for these systems. I found it very helpful myself when doing development at Oculus, just being very quickly able to find inverses, change order of operations, fix different kinds of bugs that happen. Very often you can get things working most of the time and then doing something catastrophically bad. Like maybe the yaw and the pitch will be aligned correctly and then the roll is backwards for some reason. A lot of things happening like this, and these are the kinds of tricks I think that are helpful. The kind of insights, let's say, that are helpful, that can save you a lot of time and trouble. So if we go T inverse, well, the first thing I would like to do is undo the translation, right? Because that was the last thing applied. So to undo the translation, I'll put it over here. I'll make a matrix that undoes the translation If I want to make a perfect matrix that undoes the translation, what should go inside of here? The identity rotation, which also just looks like the rest of an identity matrix. So that just undoes the translation. That gets applied first, but remember that I'm going from right to left. That's why I made a big deal out of that as well. So we're going from right to left. That gets applied first, and then we come over here. And in this case, we undo the rotation. So I have my R transpose there, and then I fix the rest of this matrix here. I had better not do any translations here now. This is a pure rotation. So I just put zeros. And I complete the bottom in the same way always for these. I don't need to multiply that out and simplify it. You can go ahead and do that. There's not, this is a fairly generic matrix here anyway. So I like to keep it in that form. So once again, to summarize, T is rotation, then translation when applied to a point, and T inverse is inverse translation then inverse rotation. Okay? Questions about that?